Chapter 9, Introduction to the T-Statistic, Part 4. In Chapter 8, we noted that one criticism of a hypothesis test is that it does not really evaluate the size of the treatment effect. And when we're conducting a hypothesis test, that is our interest. We are interested in determining if the treatment does have an effect, and as a result, does shift the average value of that population either upward or downward. Instead, a hypothesis test simply determines whether the treatment effect is greater than chance, where chance is determined by the standard error and the alpha level. So again, we determine what those critical z values are based on our alpha, one-tailed, two-tailed test, and the calculated value of standard error. But we also recognized and saw that mathematically, the standard error is a function of sample size. So in particular, it is possible for a very small treatment effect to be statistically significant, especially when the size is very large. So again, as a quick review, when we calculate our z statistic, we take our sample mean minus mu divided by our actual standard error of the mean. And the standard error of the mean is equal to the standard deviation of the population over the square root of n. And we learn the relationship, and hopefully it is now ingrained in your brain, that as n increased, standard error decreased, and z-scores increased. And as z-scores increase, the likelihood of rejecting the null also increases. So again, once we recognize that the standard error is a function of sample size, we can see that there is a slight flaw in the hypothesis test when we are using those values to determine that if something is statistically significantly different. As a solution to this problem, it was recommended that hypothesis tests also report or be accompanied by an effect size measurement. And we learned how to calculate Cohen's d. And Cohen's d expresses the mean difference in standard deviation units. So again, opposed to the z-score, in this case, expressing the mean difference in standard error units, where standard error units is influenced by sample size, Cohen's d is simply expressing the shift, the difference between the treated mean and the untreated mean in standard deviation units. So just to review, here's more information on Cohen's d. The original equation included the population parameters. Our estimated Cohen's d is computed using the sample standard deviation. So down here, now in this chapter, we'll see the verbiage used estimated d. And the reason is because now we're working with sample statistics as estimators of the population parameter. When we were conducting a z-test and computing Cohen's d, we just referred to the value as Cohen's d. It was not estimated because we actually had our standard deviation of the population. So just to review from the last chapter, d was equal to m minus mu divided by the population standard deviation. So again, that is applicable to, that was chapter 8 for a z-test. But now in chapter 9, one of the reasons why we would utilize a single sample t-test opposed to a z-test is the fact that we do not have the population standard deviation. And consequently, we have to use a sample statistic, the sample standard deviation, as an estimation of the population standard deviation. So this is our new equation, estimated d, and sometimes we'll just simply abbreviate estimated d is equal to the sample mean minus population mean over the sample standard deviation. And again, what we're doing is taking this mean difference, remembering that the null says that would equal 0, that there'd be no difference, no shift, no change, no difference. We take that mean difference and divide it by the sample standard deviation And when we divide by a specific unit, then we're expressing the quotient, right, that the end result in those same units. So now we're taking the mean difference and dividing by standard deviation so that our estimated Cohen's d is an illustration of the mean difference between the treated group and the untreated group, and it's expressed in standard deviation units. So we can think of it as, the original untreated population looks like this. Let's just make up numbers. This is an average of 100. The treatment group, which is a representative of the treated population, shifts over. The average now, let's say, is 115. And so now we're expressing that difference of 15 points. That's a raw score difference. But now when we calculate estimated D, we're going to express that difference in standard deviation units. You can think of it as z-scores. How many z-scores did it shift upward or downward? And then we learned about the table that determines what is considered a small effect size, medium, and large. Anything above 0.8 is considered a large effect size. So I'll just stress that once we draw our conclusions, it is useful to include a measure of effect size to help support those conclusions. So if we reject the null hypothesis and calculate Cohen's d, we hope that that Cohen's d is fairly large to affirm that we've drawn the accurate conclusion. So as I've stated before, calculating Cohen's d can illuminate or highlight whether or not you've engaged in a type 1 or type 2 error. Again, a type 1 error says that you say there's an effect size when there really isn't. And a type 2 error occurs when you say there is not a treatment effect when there really is. And those errors can result from the sample size, either too large or too small. So we will always draw our conclusions based on our critical values, and then that those are the conclusions that we will draw, and we do so accurately. But the supporting statistics will help us determine, was our sample size so large that it made us believe there was a treatment effect when there really wasn't, or vice versa. The sample size was so small that it didn't detect true effect size, and we failed to reject the null hypothesis. So again, the measures of effect size are very important as supporting evidence to bolster the conclusions that you have drawn. In the previous video, we walked through example 9.1, which related to the research on infants staring or spending time looking at what was deemed an attractive face opposed to an unattractive face. And in that hypothesis test, the null stated that the infants would have no preference for the different type of face. We walked through the 4-step process, and our conclusion was that our t-statistic allowed us to reject the null hypothesis and conclude that there was a difference in the amount of time that the infants spent looking at these different faces. And in fact, they tended to spend, on average, more time looking at the attractive face opposed to the unattractive face. And we were given some sample statistics for that study. So we were given values of the average amount of time they spent looking at the attractive face, which was 13 seconds. Remember that the null, the average amount of time expected if the null were true, was 10 seconds, because they spent a total of 20 seconds staring at these faces. If there's no preference, which the null says there's no difference between the amount of time they look at either face, if we take that 20 seconds and divide it by 2, because there are 2 different categories, attractive, unattractive, then we would presume that the infants would spend an equal amount of time on each face, so that would equal 10 seconds. The sample, though, of 9, I believe it was 9 infants, was that they spent an average of 13 seconds looking at the attractive face. So that's some of the data that was provided for us when we conducted this hypothesis test. And we were also told that the SS, the sum of squared deviations, was equal to 72. With that statistic, we were able to calculate our variance. Our variance was equal to SS over degrees of freedom. If we replace variables, variance is equal to 72. Degrees of freedom is equal to n minus 1 is equal to 9 minus 1, which is equal to 8. So 72 divided by 8, our variance is equal to 9. And therefore, a standard deviation is the square root of our variance. Square root of 9 is equal to 3. And that's what's illustrated here. We've set the mean here in the center, and the standard deviation is equal to 3 points. Again, standard deviation represents the average difference between the mean and the other scores in the distribution. In other words, collectively, these 9 infants spent 13 seconds looking at the attractive face, but not all of them spent 13 seconds. On average, they spent 13 seconds plus 3 minus 3. So again, centering this range that is representative of the center. Okay, so every value isn't going to be identical to the mean, but within a certain range, we would say it's close enough where it resembles the mean almost exactly. So now here we're illustrating the center, the average amount that they spent looking at the attractive face, and then the average difference, plus or minus, away from that. Notice that that's capturing the majority of those 9 scores, right? Anywhere from 10 to 15 seconds spent looking at the attractive face. And then we have some outliers that are represented by 8 seconds, and then 2 that were represented by 17. So a lot more time spent looking at the attractive face compared to the average amount spent. As indicated previously, if there were no preference, as stated by the null, the population mean would be equal to 10 seconds. And that's what we have identified down here, that the average amount of time spent on either face is equal to 10 seconds. And notice again, that's stating a value from the null. The null would say equal amount of time, 20 seconds total, 2 faces, 10 seconds per face. So that's where the untreated population mean would be centered. Therefore, the results show a 3-second difference between the mean for the sample here and the mean for what we refer to as the untreated population. That value coming from the null. No difference in time spent looking at the attractive versus the unattractive face. So the difference between 10 and 3 in raw score points is 3 points. So that's the mean difference. And now, instead of expressing that mean difference in raw points, we want to express it in a standardized measurement, in this case, standard deviation units. So our estimated Cohen's D equation says that we take the sample mean minus the untreated population mean and divide by the standard deviation of the sample. So if we replace variables, or estimated, sorry, should include D here, estimated D is equal to 13 minus 10 divided by our standard deviation of the sample, which was equal to 3. So we have estimated D's equal to 13 minus 10, 3, divide by 3, and we get estimated D equal to 1. So we're saying that 3-point shift is equivalent to 1 standard deviation unit. In other words, the attractive face, or this quasi-independent variable, right, they're looking at one face opposed to the other, they shift in the amount of time that we would expect if the null were true by 1 whole standard deviation unit. And according to the table that was presented in Chapter 8, anything above 0.8 is considered a very large effect. So having calculated this supporting statistic or measure of effect size, we now feel confident that the conclusions we drew in the previous video, which was to reject the null hypothesis, is supported by this measure of effect size. It's estimated Cohen's d. Again, in step 4, we drew conclusions and based on our t statistic, and just as a reminder, our t was equal to 3.00. Our critical t was equal to positive negative 2.306, and based on the location of our t statistic, it was well into the critical region, which enabled us to reject the null hypothesis. We reject the idea that the infant spent an equal amount of time staring at the attractive versus unattractive face. We conclude that there is a difference, and this measure of effect, estimated d, supports that conclusion that we're saying the mean difference expressed in standard deviation units is equal to 1 whole standard deviation unit. And given the parameters presented in Chapter 8, the table indicates anything above 0.8 is considered a very large effect. And so now we've conducted this hypothesis test, we've drawn our conclusions, and we've included a supporting statistic so that we feel very confident in our conclusions to reject the null hypothesis. An alternative method of measuring effect size is referred to as R-squared. R-squared represents the amount of variability. Again, variability means change or difference. So R-squared represents the amount of variability in scores which can be attributed to or explained by the treatment effect or difference in quasi-independent variable categories. So again, R-squared is expressed as the amount of change or variability in scores which is a result of treatment or difference in quasi-independent variable conditions. And we calculate R-squared by taking the variability counted for by treatment or difference in quasi-independent variables conditions and divide by total variability. And that translates into this equation here. T squared, so again our t statistic, we calculated that previously. That's how we conducted our hypothesis test, was the sample mean minus population mean divided by the estimated standard error of the mean. So at this point, again, recognizing that measure of effect would be calculated after the hypothesis has been conducted, the hypothesis test has been conducted, so we will have our t-value, and we can simply enter into this equation. So for this statistic, R-squared, we would simply replace variables. R-squared is equal to our t statistic, which for this example, t was equal to 3.00. So 3.00, we're going to square that over t squared, so 3.00 squared, plus degrees of freedom. Again, our sample size was equal to 9, therefore degrees of freedom, n minus 1 was equal to 8. So we would add this to a value of 8, so we just do our calculations. 3 squared is equal to 9, and this would be 3 squared, 9 plus 8, so 9 over 17. So in our calculators, enter 9 divided by 17, and we should get a value of 0.5294. And we can express that, given the definition, as the percentage of variability or change in scores explained by the treatment or difference in quasi-independent variable categories. So we would simply express this multiplied by 100 and express it as a percentage. So given this calculation, again, I've just rewritten the values that we just went over. R squared is equal to 0.05294. Whoops, I'm sorry, that's not correct. Pardon me. It's 0.5294. If we multiply that by 100, we're saying that it's 52.94%. And now I'd like to verbally express what that value represents. So we can say, let's just round to 53% for purposes of easy math, and you'll see why in just a second. So we would say that approximately 53% of the change in scores is attributed to the difference in test conditions. And those test conditions were the unattractive face versus attractive face. So in most cases, we would, if a treatment is administered, we would say that in this case, 53% of the change in scores is as a result of the treatment. In this case, a treatment really wasn't administered, so we have to be conscientious of that when we are expressing what these values represent. So in this case, we would say 50% of the change in scores. Again, we anticipated no difference in the amount of time spent looking at the different faces, when in fact the sample illustrated that there was a 3-point difference. So we would think of it as everyone's score increased by 3 points. 53% of that change in scores, the amount of time they spent looking at one face versus the other, was attributed to the fact that there were different faces, that the conditions were unattractive, attractive face. And because there's a difference, that promoted or prompted a change in scores, a change in time spent at looking at one face versus the other. And in this case, they spent 3 minutes longer on average on the attractive face opposed to the unattractive face. So again, we would express this, and again, this is approximation. The value we calculated given our equation was actually 52.94%. We're going to express it as an approximate amount, 53% of the change in scores, 53% of the change in time spent looking at one face versus the other was due to the fact that there were different faces to look at. I hope that makes sense. Normally we would simply say due to treatment. If treatment is they were testing the effect of a drug, the treatment would be that they received the drug. So just changing the variable, so hopefully this makes sense. If it was a test of a drug, we may say 53% of the change in depression scores was due to the treatment being given, that they were given the drug. Again, this example doesn't fit that standard phrasing because there's no treatment being administered. We're really just looking at the different conditions, which is described as a quasi-independent variable, attractive versus unattractive faces. Now, something to consider is what's the difference between 100% and 53%? So that would be 47%. So we can think of the remaining amount of difference, 47% of the difference is attributed to other factors. So there may be other things at play here. So we recognize that obviously it's not 100% of the change in scores is as a result of the different quasi-independent variables. There's something else going on that we're not necessarily testing. Nonetheless, we're given a table, just as we were with the Cohen's D, to determine what would be considered a small effect, medium effect, or large effect. So anything above or at 0.25 or 25% of a change due to treatment or difference in quasi-independent variable conditions is considered a large effect. Sorry, I had a little brain freeze there. So again, anything above 0.25 or 25% of change attributed to what we're testing, whether it's a treatment or difference in quasi-independent variable conditions, is considered to be a large effect. So here we would conclude that approximately 53% of the difference in the amount of time that these infants are spending looking at these two different faces, that is a very large effect. And the reason there is a difference, the researcher is saying, they're contending that it's because they have the option of looking at one face versus the other, one condition versus the other. And the researcher hypothesized that the infants will have a preference for one over the other. And now we're saying that, yes, indeed, they are spending more time looking at one face versus the other. And the difference in time is attributed to the fact that one's considered attractive and one is considered unattractive. So again, this is an additional measure of effect, and we'll see it used in the different t-tests. We can calculate it with a single sample t-test, or in Chapter 10, when we learn about the t-test for independent samples, and then in 11 for repeat sample t-test. So again, it's a measure of effect, and normally the researcher would rely on one or the other, either Cohen's d or r squared. It would be unlikely that the researcher would use both, but for our purposes of an introductory statistics course, there'll be cases where we calculate both for one example, just to affirm that if you have a large Cohen's d value, you should also have a large r squared value. An alternative technique for describing the size of a treatment effect is to compute the estimate of the population mean after treatment. For example, if the mean before treatment is known to be a certain value, a mu equal to, in the case of the infants, equal to 10, and the mean after treatment, or difference in quasi-independent variable conditions, is estimated to be 13, then we can conclude that the size of the treatment, or the difference due to the quasi-independent variable conditions, is 3 points. Now, we're going to try to estimate what we would anticipate in the example of the infants looking at these different faces, what the average amount of time spent on the attractive face would be if we had access to all infants in the population. So we want to estimate what mu is equal to. So again, the confidence interval is an alternative technique for describing effect size. It estimates mu from the sample mean. Again, if we're selecting a sample, inferential statistics says that we can use that to infer something about a population. So now we're going to try to estimate what the true treated mu would equal, or mu of the quasi-independent variable condition would equal. And it's based on the reasonable assumption that m, the sample mean, should be close to the population mean. The interval constructor defines near based on the estimated standard error of the mean. And finally, we can confidently estimate that mu should be within that located range of values. So our equation for calculating the anticipated treated mu, or mu of the quasi-independent variable of interest, is equal to our sample mean, right? That's an estimate of what we would anticipate the population mean to equal. Again, inferential statistics means we use sample means to draw conclusions about a population. So we're using this value to estimate what the true population mean would equal. So our equation is mu is equal to the sample mean plus or minus t multiplied by the standard error of the estimate. And now we kind of break this down. Again, this is our sample mean. We know that this is estimated standard error. And though we may believe this is our t-statistic, it is not. This t-value comes from the confidence percentage and is found in the t-table. So don't make the mistake of entering your T statistic. That is not the T statistic. This T comes from the confidence interval range that is set by the researcher. Common intervals are 80%, 90%, 95%. And what that indicates is once we compute this value, we would say that we're 80% confident that the true treated population mu resides within this range that we just calculated using this equation. Or we may say we're 90% confident that the true treated population mu is going to fall within this range that we just calculated. Again, in this case of the infant spending time looking at the different faces, we would say that what we're calculating is the true population average of infants spent looking at the attractive face. So the mu, and we could denote it as mu. So again, what we're calculating is if we had access to all infants, if we could test all infants in the population, what we're trying to determine is what is the average amount of time that they would spend looking at the attractive face. So we're going to use this equation to come up with an estimate, a range of values. So given our equation, visually this is what it would look like. In the center of this distribution that I've drawn is the average amount of time spent looking at the attractive face for those 9 infants in the sample. And again, this is used to estimate mu attractive if we had access to all infants and we were able to test all infants. So again, note that this value here, right, is in the center, and then it's plus or minus the product of this value. So that's going to give us a value below and above the sample mean and create a range, right? So we're going to have a value here and a value here, and given whatever percentage, let's say we're 80% confident that once we do the calculation, we'll have a value. Again, this was 13 seconds. So we'd have a value less than 13 and a value greater than 13. And we can conclude then that we're 80% confident that if we had access to all infants in the population, they would spend an average amount of time looking at the attractive face that falls within this calculated range using this equation. So we're actually going to work that out using 80% as our confidence level to see the steps of how we compute this particular range that we refer to as the confidence interval. So again, by definition, the confidence interval is an interval or range of values centered around the sample statistic, the sample mean. The logic behind a confidence interval is that the sample statistic, such as the sample mean, would be relatively near the corresponding population parameter, mu. Therefore, we can confidently estimate that the value of the parameter should be located within that interval or range. So let's walk through the example using the infants and the amount of time they spend looking at the attractive face to illustrate this new concept. Okay, so a quick review. The research that we are looking at is to test whether or not a group of infants, 9 infants in fact, are going to spend a different amount of time looking at an attractive face opposed to an unattractive face. So the data that was given that we've been working with was a sample of 9 infants. The degrees of freedom was equal to 8. The average amount of time spent looking at the attractive face was equal to 13 seconds. The variance cited was 9. Estimated standard error was equal to 1, and it produced a t-statistic of 3. Now we're going to calculate using 80% confidence interval. So what we're going to do is create a range of values that we're 80% confident that the true average amount of time spent looking at the attractive face will fall within. So our equation for mu attractive, is equal to sample mean plus or minus the t multiplied by the estimated standard error. Let's just replace variables that we know right now and find out what we need to solve this. So our sample mean was equal to 13 seconds plus or minus, and t, again, as I stated earlier, it is not our t statistic. We're going to find that using that 80%, and I'll show you how to do that in just a second. So I'm just going to leave that as is, and we multiply it by the estimated standard error. Just to keep this a little cleaner, I'm going to put those in parentheses. So estimated standard error was equal to 1. So what's missing is that t. How do we find the t? So visually we're going to draw out what we are solving for. We want to anticipate what the average population amount of time would be for infants staring at the attractive face. Again, given this equation, the sample mean is in the center, and this represents mu attractive, the population average time spent by infants looking at the attractive face. Now we know that that's a good estimate of what we would anticipate the population equal, but we know samples aren't always perfect. So we're going to find a range of values that we feel 80% confident that the true attractive average or average amount of time spent looking at the attractive face will fall within. So we're going to calculate a value here and here, hence the positive and negative, or the addition or subtraction of that product of t multiplied by the estimated standard error of the mean. So how do we find the t? Okay, so we're saying 80% of the values will be in the center, centered around 13. That leaves 20% in the tails. So we're going to convert that 20% into a proportion. So we divide that by 100. And we get 0.20. So now we're going to utilize our t distribution to find out what the t value is in this equation. So here is our t table. Now when we're computing, it's important to note, and please write this down in your notes, this is very essential, that when we're calculating confidence interval, regardless if we originally did a one-tailed or two-tailed test, the confidence interval is always a two-tailed process, and the reason is because we need a value above that center value and below. So again, I'll restate, regardless if your initial hypothesis was a one-tailed or two-tailed test, the process of computing confidence interval will always be a two-tailed process, meaning that we use this tier that I just put the arrow by. So now we're going to look for a proportion of 0.2 in the tails because we're looking for the value of 80% in the center, and our degrees of freedom, right, was equal to 8, so we're just going to see where those values intersect with one another, and we get a value of 1.397, and that's the t value in this equation. Again, it was based on centering that confidence proportion in the middle, and the leftover from 100 in the tails, looking at that proportion using the two-tailed tier in our table, and degrees of freedom. So now we've determined from our table that this t value here and here is equal to negative 1.397 and positive 1.397. Again, we're going to use both versions of that value in our equation to calculate what the anticipated mu would equal the anticipated average amount of time infants will spend looking at the attractive face. So I've simplified the diagram to make things a little easier to see. So again, our equation is mu attractive, the population amount of time spent looking at the attractive face for these infants is equal to the sample mean plus or minus the product of our t value multiplied by the estimated standard error. Again, if we replace variables, this is 13 plus or minus, and we just found our t value. Again, it's not the t statistic, it's the t that comes from the proportion in our t table, and that was 1.397. Again, this plus or minus takes care of the negative and positive version, and then multiply by estimated standard error, which was equal to 1. So we would say that 13 plus or minus 1.397 times 1, 1.397. So again, notice that the 13 is in the center and we're adding that value and subtracting to calculate the anticipated population mu. So if we add that product to 13, then we would get a value of 14.397. If we subtract it from 13, we get 11.603. And what we've just calculated is a confidence at 80%. And what we're saying is that the researcher is 80% confident that the true population mu resides within the range of 11.603 seconds and 14.397 seconds. In other words, that if we had access to all infants and were able to engage them in this type of research and calculate the average amount of time they spent looking at the attractive face, we're 80% confident that the population average amount spent looking at the attractive face would range anywhere from 11.603 seconds all the way to 14.397 seconds. Again, and it was all based and centered around that one sample of 9 infants that spent 13 seconds looking at the attractive face. So now we're saying that we would expect the true population average to fall within this range, and we're 80% confident that that would be the case. Now I'm going to walk you through an example using the same values and use 90% confidence interval. And I'm actually going to do an example of 95% and 90% in a different video so that we can end this one and continue discussing the elements of a confidence interval and the influences on the confidence interval. So that concludes this part of Chapter 9 lecture.